All right, welcome everybody from our home page. If you're not there yet, go to P3, go to modules, and then go to bell ringer. So this one seems simple enough. It asks us to write an expression. So this is a basic principle of algebra. An expression is just a collection of numbers and variables. That's it. So even a number by itself, like 3, can be considered an expression. It's something that can be part of an equation. Now the difference between an equation and an expression is that an equation, it's right there in the name, an equation has an equal sign. So x plus 2 equals 3, that's an equation because it has an equal sign. But that's not what it's asking for. It's asking for an expression. So an expression is just part of an equation. It can be a number by itself. It can be a number with a variable. It could be a number added to another variable, subtracted from a third variable. It's just a series of numbers and variables put together in a row. So this tells us to write an expression that is 2 times a number subtracted from 8. 2 times a number subtracted from 8. So we have a 2 and then a number. Here it says take the number to be x. So here you have to draw the parallel between, here it's asking you to do a number, and down here it's telling you that it wants that number to be x. So 2 times a number. We can do 2 times x like that, but it's much easier and more concise and clear to just do 2x, which means the same thing. When you put two things right next to each other in algebra, that means multiply. Now, it says that the expression should have 2 times a number subtracted from 8. Now, I know some people might be tempted to write this, but that's actually wrong. Don't do that. It's not saying 2 times a number and then subtract 8. It's saying 2 times a number subtracted from 8, meaning that we have 8 and we subtract 2 times a number from that. So this is the expression it's asking for. So not too complicated. You just have to know how to read the question and understand the principles of taking word descriptions of an expression to writing an actual expression. So the final answer down here is eight minus 2x. Save and submit. Make sure you get that in. I'll give you a minute to do so before we move on. Once your bell ringer is submitted, scroll down to the bottom of your bell ringer, click next to go to our class breakdown. So our objective for today is that we should be able to describe the effect on a scaled copy when you use a scale factor that is greater than 1, a scale factor that is less than 1, or a scale factor that is equal to 1. Now, I've already touched on this before, so those of you who've been following the unit work so far, this will probably seem really simple to you. But we also need to be able to describe how the scale factor that takes figure A to its copy, figure B, is related to the scale factor that works the other direction. So we're going to be doing a lot of the same work we've already done. We're just going to figure out how to do it, how to reverse it. So if we scale something up, and then we take the scaled copy and scale it back down, we're going to go back and forth, and we're going to see how these two things are related to one another. We're going to see that there's a direct relationship between scale. If you scale one way, how do you reverse it? That's the question. So we did our LEAP practice bell ringer. We are now going to, I know this is like the 4th time, but I've been assured that it's supposed to work this time. So we have to go ahead and take our I-steep. So everybody, follow me to do, what's that? You already know how to do it? Okay, so I'm gonna go ahead and put this up on the screen. If you don't know how to do it, then watch the screen while I go through this real quick. You need to go to your ClassLink page. Log into ClassLink, click I-steep. Make sure your name is correct at the bottom. Screening, math, computation fluency. Once you get to this screen right here, wait. Those of you who are in my classroom, once you get to this screen right here, wait until I say go. We're all going to take it together.
Is it supposed to say your name?
It's supposed to say my name and then your name. What does it say?
Mine say my first period teacher.
You know what? We're just going to go with it. If it says your homeroom teacher, that's good enough. If it says my name or your homeroom teacher's name, either way, we're just going to go with it. So people watching from Zoom, you need to take care of this as quickly as possible.
He said we have always.
Is that your first period teacher? Yeah, Miss Robinson across the hall. It's gonna go. Okay. We're gonna maybe it's supposed to say your homeroom teacher, but as long as it says your name, that's what matters. That means we can find the data. Did you click math and not English? Okay. Did everybody sure you click math and math computation?
I tried it twice to make sure.
Okay. All right. So if you're on Zoom right now or you're watching this video later, when you try to take the I-steep, you may see your homeroom, you may see a different teacher's name than mine. As long as your name is here and you're sure that you've gone to math, #1 computation fluency, then we're just going to go with it. Yes, Jeffrey.
Which one? 1, 2, or 3?
1, computation fluency. Okay, those of you on Zoom right now or watching this video later, you need to make sure you take your I-steep as soon as possible. Now, for those of you who were not in my classroom to do it with us, the very next thing after the class breakdown is some specific I-steep instructions. I know looking on the video, it's hard to read, but it's step by step. Go to ClassLink, click on the I-steep icon, check to see that your name appears at the bottom of the page. Click on screening, click on math, click on #1, computation fluency, and then click start to begin and click submit when finished. So straightforward instructions on the Canvas module for today. I will leave those up with today's work, but on your own time, those of you who are not joining me in class live today, you need to make sure you take care of this. So if you're taking care of your I-steep, let's move on to 1.5, the size of the scale factor. So this is our main lesson for the day. You need to find the online workbook and click take me to the website. So let's do this. First, it wants us to solve some simple equations. Now, later you'll see why it's asking us to do this, but for now, we're just going to roll with it. So, does anybody in the chat or here want to give me see if you can do some mental math? Tell me, 16x equals 176. And now some of you are still struggling with algebra, so that's the same thing as 16 times a number we don't know, x is the unknown, equals 176. What do y'all think? Anybody have any guesses? Okay. Well, there's two ways, well, there's multiple ways to do this, but the most obvious ways, there's the long way, which is get the x by itself. That's called isolating the variable. Or there's the mental math way. I'm going to show you both ways. So if we have 16x equals 176, we have to divide both sides by 16. This is the long way. These 16s cancel out, which leaves x by itself. And now we just have to do 176 divided by 16. So how many times does 16 go into 17? 1. 1 times 16. And then we got that down. And then 16 goes into 16 one time. So x equals 11. So that's the long way. That's the long way. Got a question on Zoom real quick. That's the long way. But the short way, the mental way, it asks you to solve them mentally. So let's see if we can find the mental shortcuts for these. So in my head, I know 16x equals 176. That means 16 times what equals 176? In my head, I can say, well, 16 times 10, but it is 11. We already figured that out. But I'm showing you the mental math tricks. I can say in my head, well, I know that 16 times 10 is 160. That's easy. And in my head, I know that 16 times 1 is 16. And if I add these together, that's 176. See? So it's 11. So that's the mental math way. You see how I did that? Okay. Because 16 times 10 is easy. Just add a 0 after it. And 16 times 1 is easy. It's 16. Any number by times 1 is the same number. So that's the mental math trick way. So let's see what we can do with some of the rest of these. 16 times x equals 8. Think about some of the scaling work we've done the past couple days. What do you think? What could we take 16 times what to make 8? We can do it the long way, but is there a quicker mental way? What is the relationship between 8 and 16?
2.
There is a factor of 2, sort of, but if we do 16, hold on, if we do 16 times 2, that's going to give us 32. That's going to make us go up. So we need to do 16 times, not 2, but what's that? 1/2. There we go. Because 8 is half of 16. And so we've already practiced this with our scaling. We know that we can do this. 1/2. Now the long way gets us the same answer. So that's the mental way. Just going, wait a minute, 8 is half of 16. So if I do 16 times 1/2, I'll cut it in half to 8. That's the short mental way. The long way is what we did before. If we divide both sides by 16, we make these 16s go away, we got x by itself, and then this fraction, 8/16, simplifies down to 1/2, because we can divide 8 by 8 to get 1, and 16 by 8 to get 2. So 8 reduces to 1, and 16 reduces to 2. You see that, Kamora? Okay, so that's the long way. All of these have the longer way and the shorter mental math way, and that's what we're practicing right now. All right. The next one, this is kind of weird. 16x equals 1. Think about this. If I have a pizza and I cut it into, so that's 4 slices, 8 slices, and now 16 slices. So each one of these slices is 1/16. See how that works? And if I put all 16 slices together, that would be 16 out of 16, which is 1 whole pizza. So think about that right here. 16 times what equals 1 whole? Not 16 times 16, but what? 1/16. There we go. Because if I have 16 slices of pizza and each slice is 1/16, that gives me a whole pizza. Everybody understand how I did that? So in this case, x is 1/16. And again, we can do it the long way, which is we divide both sides by 16. These 16s cancel out, and we're left with x equals 1/16. It's the same process. But being able to do these things mentally and think about models like this, that 1/16, if I have 16 of those, that makes a whole. So 16 times 1/16 is 1. Being able to do that mentally without having to write it out is going to help you a lot in this unit. That's why we're practicing these things right now. All right. This one's a little bit backwards. 1/5 x equals 1. Very good, Maura. It is 5. So by the same principle as we did it the other way before. We did 16x, that was the one above. 16x equals 1. That means x is 1/16. So this works both ways. Works both ways. This right here is, if I have 16 slices of pizza in 1 whole pizza, how big is each slice? That's what the x represents. Each slice is 1/16 of a pizza. Here it's backwards. If I have slices that are 1/5 of a pizza, how many slices do I need to make a whole pizza? 5 slices. See how that works? It's the same basic principle, just working in opposite directions. Okay? And I'm going to show you something real quick that may help you understand this even a little bit better, especially when we're working with fractions on fractions, which we will in the next problem. Check this out. We have 16 times 1/16 equals 1. If we did that from a multiplication perspective, remember, when we're multiplying fractions, we can take any whole number and express it like that. 16 is the same thing as 16 over 1. It's the same value, right? Now, if we do straight multiplication with that, so this is 16 times 1 over 16. This is 16 over 1 times 1 over 6, but these are the same value. So 16 times 16 is 16. 1 times 16 is 16. And that reduces to 1. Same process. So anytime you have a number, anytime you have a fraction and you multiply it by the same fraction reversed, it cancels out to 1. That's what we're going to see right here. 2/5 x, the last problem at the bottom right here. 2/5 x equals 1. It's not 10, but you're on the right. You're thinking. Your thinking is good here. Think about this right here. Think about what we just did. 16 over 1 times 1 over 16 equals 1.
What?
Look at that right here and tell me what I need to put here.
10.
What's that? But I heard it over here and here. 5 over 2. Because when we're multiplying fractions, if we multiply any fraction times its reverse, it equals 1. Because 2 times 5 is 7. Sorry, not 7. I'm adding there. I'm sorry. 2 times 5 is 10. And 5 times 2 is 10, which reduces to 1. So this principle is, if you understand this, then the rest of today's lesson is going to be smooth sailing, and you're going to do your exit ticket just fine. Any number, doesn't matter what it is. Because even a whole number like 16 can be written as a fraction. You take any number or fraction and you flip it to its opposite fraction, it comes out to 1. Doesn't matter what it is. Let's do something crazy. We can do, 134 over 586. We multiply that by 586 over 134. What is that going to come out to? 1. 1. It's always going to reduce to 1. Just like this and this. Any fraction multiplied by its opposite fraction equals 1. Doesn't matter what the numbers are. It's always 1. Always. Any questions about any of that? Okay. So let's move forward. Y'all are doing great. There's lots of things we gotta jump ahead on. Okay, so this asks us to do some basic scaling work like we've done all week. So what is the scale factor from the original triangle to its copy? Well, we got to get some measurements first. So this is, it's only 1 square, yes. So we're going to put that in our calculation. So this right here is 5. And this is also 5. So this is a right triangle. And it's an isosceles right triangle because these are both the same length. And here, this is 1 and 1. And we don't need to do this length because if we get these two right on an isosceles right triangle, they'll just connect. What's that? Right. Right. This is basically, I mean, if this was like this, it would be a full square. This is basically an isosceles right triangle is a square cut in half diagonal. Okay, so let's do what we've been doing all week, and let's apply the ideas we just practiced on those mental math exercises we were just doing on the previous screen. In our original, okay, I'm gonna do color coding for you.
Is that on?
You got to keep scrolling down. This is part 4, 5.4. All that other stuff requires me to pass out cards, and I can't do that because we're not supposed to be working with paper and things that pass germs back and forth. Okay, so in our original, we have the measurements 5 and 5. And then in our copy, we have 1 and 1. So this asks us, what is the scale factor from the original to the copy? Well, thank you, Kimura. You got it right away. It's 1/5. Because as we just practiced on the previous screen, any number times its opposite fraction equals 1. Doesn't matter how big or small the numbers are. Any number multiplied by its opposite fraction comes out to 1. Okay? Very good. So, let's go down to the next one. The scale factor from the original a lot of this is practicing skills we've done before. The scale factor from the original trapezoid to its copy is to draw the scale copy. Now, I'm going to draw it up here. I'm not expecting you to draw it on your screen. Again, if it weren't for the germ restrictions, I'd be passing out graph paper and you'd be doing this on graph paper. So, we got to apply the principle we practiced yesterday. We have these weird shapes that don't follow the grid. We got to draw our little lines through the middle. So right here and right here, because this is 3 and this is 3, and they intersect at 1 and 1. So there's 2 on this side, 2 on this side, 1 on this side, 1 on this side. So I can use that to make a scale copy. So it tells us that the scale factor is what now? Scale factor from the original to its copy is 2. So what am I going to do to this 3? What do you do with the scale factor always? Starts with the M. Multiply. So 3 times 2 will give me my copy, which is 6, which means that I need to make my lines 6. Now here's where things get a little tricky. We didn't do this yesterday. We got to get our point of intersection straight. Because yes, these lines, in terms of overall length, these lines are 3 and 3. But in terms of where they meet each other, there's 1 on this side and 2 on this side, 1 on this side, 2 on this side. See how that works? So we have to scale those as well. Which means that if we're going to break this down, the overall length should be 6, yes, but whenever we're determining how these lines meet, we have a 1 and a 2 to deal with. And that has to be the scale factor as well. So real quick now, where there's 1 over here and 2 over here in the original, it's the same this way, 1 here, 2 here. In our scale copy, it needs to be 2 and 4. Is anybody confused? Because I know this is a little bit confusing. It should make more sense when I draw it. So now I'm going to draw the copy. So I know that the line needs to be 6 squares long. It's going to be much bigger. Okay, so there's my top to bottom line, 6. And then I know the other line is going to be 6, but I got to make sure it's in the right place. If from here to the point where they meet is 1 on this, from here to the point where they meet needs to be 2 on this. So, and then I've got to have 2 over here. Okay, y'all see how I did that? So I know these numbers are really small and hard to read, but this line is 3, this line is 3. Where the lines meet, there's a 1 on this side, a 2 on this side, a 1 on this side, 2 on this side. Apply my scale factor. So now I have this line is 6 and this line is 6, but in terms of where they meet, I've got 2 on this side, 4 on that side. That's these right here. 2 on this side, 4 on this side. So that way I know that this is a scale copy. Any question about that? Yeah, and this line is kind of sloppy, but yeah, it works. I mean, if I could draw a perfectly straight line by hand, well, on a smartboard, it would look a lot better. But what's important is that you'll understand how I turned this into this with a scale factor of 2, which is why I multiplied it.
3 times 2, and you make big, the original 2 times big.
Mhm. This is a 2 times scale copy of this. Because, like we talked about yesterday, the 3 things that make a scale copy, the shape is the same, the angles are the same, and everything is increased by the same scale factor. Those are the 3 things that have to be the same between an original and a scale copy. If it doesn't have all those 3 things, it's not scale. All right. So now we're going to apply a fraction. Now this time it's moving backwards. It says the scale factor, pay attention, from the original to the copy is 3/2. Here, it doesn't give us the original, it gives us the copy. So we have to write our numbers different. First, let's get our measurements. This is 3, this is 3. Here to here is 6, but we want to do segments to make sure it matches. So 3, 3, and 3. It's all 3s. It's all 3s. But this is the copy, remember? Which means we got to write the equals numbers first. Here, it doesn't give us the original and the scale factor. It gives us the copy of the scale factor, which means we have to write the second set of numbers first. And then we already know that the scale factor is 3/2. So now it's kind of like a division problem. We're going backwards. Now we need to know what the original looks like. So what do y'all think? What times 2/3 come out to 3? No, 1/3. Think about it this way. If I have 2 times 1/2, that cancels out to 1, right? Because this 2 cancels out with this 2, and I've got 1 left over. So what could I put? What could I put right here? Cancel out this 2 where I just have 3 left over. 2. So by the same rule that if you take a number and you multiply it by its opposite fraction, it's always 1. If you have a fraction and you want to get this number by itself, you can multiply it by whatever number's on the bottom. Cancel, cancel.
So,
You'll see how I did that?
so,
So to go from 3 halves to 3, I can multiply all this by 2. All right. Okay. So now I know it wants me to draw the original. So I had to work backwards. It gave me, instead of giving me the original scale factor, and I got to figure out the copy, it gave me the copy and the scale factor. I got to work backwards to the original, which is all 2's. There's actually 5 2's on here, but I didn't make the whole list. So it's going to be smaller. It's going to be 2, 2, 2, 2, 2, 2. All 2's. So this was all these measurements. This is also 3. Didn't make that one. So that's all 3's. This is all 2's. Scale copy. Here it tells you what the copy is going to come out to be, and scale factor got to work backwards. So it's doing the same problem we did with the trapezoid before in the opposite direction. Okay, so now it gives us the original and the copy, and it wants us to find the scale factor. So let's do some measurements. Now we have these wavy lines. So let's do the thing we did yesterday with our measurement lines. We have a 2 here and a 4 here. And this is also a 2, and this is also a 4. Right. Now let's do the corresponding distances on our copy. This is 2, this is 4, this is also 2, and this is also 4. That's kind of weird. Well, let's go ahead and write our multiplication table anyway. Our original is 2, 2, 4, and 4. Then our copy is also 2, 2, 4, 4. So what is the scale factor here? What number can I put in all these blanks to make this true?
1.
So that's kind of weird, right? We've never done that before. When you make a copy with a scale factor of 1, what do you get? You get a copy that is the exact same. It doesn't get bigger. It doesn't get smaller. It is a same size copy. So there's a principle that I mentioned yesterday when it comes to scaling. You make a straight copy, then you want the same numbers on both because it's a direct copy. If you're making a scale copy, you either want it bigger or smaller. So if multiplying everything by 1 gives us a direct copy, this is where we have the difference we talked about yesterday. Multiplying by a number bigger than 1 makes a scale copy bigger or smaller? Bigger. Multiplying by less than 1, like a fraction, gives us a scale copy that is smaller. So that's the reason that it laid out this problem, was to put this idea in your mind. When you multiply When you make a direct copy, you want all the measurements to be the same. So the scale factor is 1 because that doesn't change any of the measurements. If you want a bigger copy that's scaled, you got to multiply all the measurements by something bigger than 1. If you want a smaller copy that is scaled, you got to multiply all the measurements by something smaller than 1. Any questions about that before we move on? All right. All right, this is a tough one because it doesn't give us the graph. So this is a situation where if you were doing this in your workbook with pencil, I would pass out rulers and we would do it that way. But since we can't do that, I'm just going to draw it and use my ruler on the board and go like that. So this line right here is really hard to do. This line right here is 6 inches. No, wait, that's a mistake. I need to do these lines in segments so I know the distance. So this right here is 4. That's from there to there. On the bottom is 2.5. That's 2.5. Now we're getting some decimal stuff. That's tricky. This little one sticking out over here is 1.5. That is 4. And that is 5.5. So we have 5 numbers, and most of them are decimals. That's tricky, but we can do this. I'm just going to take all my measurements from my original. So I have a 5.5, a 4, another 4, a 1.5, and a 2.5. And then I have to apply the same scale factor to all of them, or it's not a scale copy. So let's set up my multiplication scale table. And what is the scale factor? 3. Thank you. It's right here. 3, which means all of these have to be multiplied by 3. Which gives us, I'm going to go ahead and do these quickly since sorry. All right. So I'm going to go ahead and do these quickly for time's sake, and then I'll move out of the way. So 3 times 5 is 16.5. 4 times 3 is 12. 4 times 3 is 12. 3 times 1.5 is 4.5. And then 3 times 2.5 is 7.5. So I don't have a ruler long enough to work with me, but if I was going to make a scale, I was actually going to draw a scale copy of this with a scale factor of 3. These are the lines I would follow. The diagonal, this is going to be really messy, but this diagonal would be 16.5. And then I would go 12 and 12. And then the little line that sticks out here corresponds here. That would be 4.5. And then the line that goes down, that was 2.5 here, would be 7.5 here. Now this, what I've drawn, is not scale, as you can see. It's not big enough. It should be much bigger than this. But I'm just showing you where the numbers would go if I drew this giant scale copy of this number 4 here. What's that? Yeah. If the marker is out. See how the light is red up? See when I take this out, the red light comes on? That means it's in red marker mode. This doesn't actually do anything. Watch this. I switch them. Now the black light is lit up. See, it's black, even though this is red. This doesn't actually do anything. It's the sensors. It's like, that's why I can write in red with my finger. But that's not important. The important thing is that you understand how these measurements, which are right here, with a scale factor of 3, can be used to draw a number 4 like this that is 3 times bigger. That's the scale factor. Okay. So the size of the scale factor affects the size of the copy. If a figure is scaled by a scale factor greater than 1, the copy is larger than the original. This is third period. When the scale factor is less than 1, the copy is smaller than the original. When the scale factor is exactly 1, the copy is the same size as the original. Now, there's one principle that we need to touch on before I let you go on your exit ticket, because this is something your exit ticket is going to ask you. So everybody, Batavia,